Yeah, it's working. Okay. Okay, so for today's lesson, we're gonna look at some more collisions. So last lecture, we talked a lot about collisions with momentum and conservation of momentum. So as a review, I'm gonna put the two key formulas that we looked at last class. Okay. So first, we had our momentum formula. Does anybody know what the momentum formula is? And the class would respond, because we did that yesterday. Momentum is equal to mass times velocity. Okay, now conservation momentum. And you remember from last day, this was your initial momentum is equal to your final momentum. And by substituting these things in, we have our initial substitution from the first formula. Our initial mass and our initial velocity is equal to our final mass and our final velocity. Okay, so we're going to still be looking at some conservation and momentum stuff for this class. That's why I wrote it up there. Alright, so this class I'm going to cover a different type of another conservation concept, and that's going to be conservation of energy, kinetic energy. So, as you learned in Physics 20, we have your kinetic energy formula. And does anybody know what that formula is? Do you know what the formula for kinetic energy is?
1/2 mv squared?
Yeah, perfect. So it's 1/2 mass times velocity squared. Alright, so very similar to how we did what we did with the conservation of momentum. We're just going to work. It's exactly the same. Right here, we're going to have our initial kinetic energy is equal to our final kinetic energy. And of course, we can substitute that in. The 1/2 mi vi squared is equal to 1/2 mf bf squared. Okay, so these are the formulas that we're going to be using for today's lectures. Alright, so the important thing to know about conservation of energy is that energy is not always conserved. Okay? There are two types of collisions, where energy is conserved and energy is not conserved. And I'm going to talk about that today and how you figure that out. Okay? So the first type of collision is an elastic collision. Okay? So that's one where momentum is conserved and our energy is also conserved. Okay? Okay. So we have a second collision type, and that's inelastic. Okay? And that's one where we have our conservation momentum. Always have conservation momentum for any collision. Okay? So this is conserved. Our energy is now no longer conserved. Not conserved. Okay. So, you're probably asking yourself what exactly an elastic and inelastic collision is. So, to describe that, I brought in this handy-dandy rail car system. So, you have two cars on a rail. They're equipped with springs in the front. Okay? And they're designed so that they stay in this one-dimensional track. Okay? So the first thing I'm going to do is we're going to do a collision where one of the cars, the car on the right, is going to be moving faster than the car on the left, and they're going to be colliding with each other. What do you guys think is going to happen when they collide?
Gonna go this way?
Yeah, both cars are going to go that way?
No. They're gonna bounce back in the way they came.
But the one that was going faster will go slower backwards.
Okay, perfect. Yeah, okay. Well, as scientists, we always test out our hypotheses, so let's do the experiment. Try my best to make this one move faster. Did everyone see what happened there?
Yeah.
Okay, so our hypothesis was correct. We had both the cars collide, and the right one was moving initially faster, and when it collided, this one that was moving slower was moving faster, and vice versa. Okay, so that right there is an elastic collision. Okay? So we had a conservation of momentum and energy when these two cars collided with each other. So what do you think, how is that transfer going through? Like, what do you think is happening here? Why when we throw the faster car at the slower car to date, what's happening? Are they exchanging momentums? Not sure.
Transferring.
They are. Yeah, they're kind of like, it's sort of like a transfer of momentums. So you have your fast car. I'll draw a longer line. I forgot to say, these cars are the exact same mass. Okay? So that's why we can just say, using our formula, we have a constant mass, higher velocity, that means we're going to have a higher momentum. Okay? Lower velocity, lower momentum. Alright? So, this car 1, we'll call this one car 1, here on your left side, is our P1. And then car 2, the one that was moving a little bit slower, is on this side. And when they collide, they're actually doing a switch of momentums, a transfer, as you said. Okay, so that you can also use kinetic energy as a transfer for both of them, okay? Because this is an elastic collision. So basically, elastic collisions is any time you have two objects that collide and they bounce off each other. So another real-world example would be like two pool balls coming at each other and they bounce off of each other, right? Okay, so I'm going to do this one more time. I'm going to do the exact same thing where I have the one on the right, or your left, is going to be moving faster than the one on your right. Okay? This time when they collide, they're going to become attached to each other. Okay? So, what do you predict is going to happen after they collide?
That one moving faster?
This one's moving faster, yes.
We'll both go that way.
Okay? Alright, well let's test it out. Nice. Very nice. Okay, so just again, they're both moving this way. Now it's not a perfect system, because for perfect conservation of momentum and conservation of energy, you need an isolated system. There's a lot of restricting outside forces. Can you guys name some of the restricting outside forces that are acting on this experiment?
Friction.
Yeah, perfect. So where do you think the friction would be?
On the wheels.
Yep. Perfect. So these wheels, they do not, when I spin them, they stop. If it was an isolated system, they would spin forever. Right? So there is an outside force acting on it, and that's friction. Perfect. Okay. And that's the major one for the wheels. There's also some action with the spring. You're going to lose some energy with the springs when they hit each other. Okay, so that right there, that is an inelastic collision. So, we do not have conservation of energy, but we do have conservation of momentum for this inelastic collision. So what's happening is, and this is kind of as a review of our vector addition from which you guys did in Physics 20. Any of you took Physics 20. Is you have your two objects coming at each other, and because these are vectors, when they hit each other, they're actually going to sort of cancel each other out in a way because they're going opposite directions. So when they collide and they attach, you're going to have a final P, a final momentum. Okay? What do you think this final momentum is equal to?
P1 minus P2.
Yeah, perfect. It's P1 minus P2, and that's just simple vector addition and subtraction. Okay, so that is my demo. Oh man, we're way under time.